Well, hello again. So today we're going to start a new chapter, and this chapter is going to be on forces. So we've kind of stepping a little bit away from motion, and we're going to be dealing with forces. Okay, so what causes something to change its velocity? So we have this object that's going around, and we'll take this car, for instance. We have a car that's going to be traveling around, say it's on speed control. It's going down the highway at 70 miles per hour, and all of a sudden the car in front of it slams on its brakes. So this car is going to also slam on the brakes, and it's going to go down from 70 miles per hour to 50 miles per hour. So what causes that change in velocity? Well, it's a force. A force is going to act on the object. The object is the car. There's going to be some sort of force that's going to act on this object that's going to cause the object to either accelerate or negative acceleration or deceleration. So in the case of a car driving down the highway going 70 miles per hour and changing its velocity to 50 miles per hour, it's going to slow down by stepping on the brakes, and that is going to be a force that's going to create the change in velocity. Okay, well, what is a change in velocity? That's an acceleration. So we know that whenever we have a change in velocity, we're going to have some sort of acceleration or a negative acceleration. So we're going to have, the object is going to speed up or slow down, and what causes it to speed up or slow down is going to be a force. And that's what this chapter is going to be based on, is forces. So the SI units, the System International units that we use for forces, is called a Newton. It's named after Sir Isaac Newton, you know, the guy with the apple falling from the tree. Okay, the Newton is symbolized with a capital N. So when we say how many forces are acting on it, we're going to say it's 10 newtons, and we're going to use 10N. A Newton is broke down into simpler SI units, which is a kilogram times a meters per second squared. And if you break this down even further, you know that kilogram is the SI unit for mass, and meters per second squared is the SI unit for acceleration. So we can tell just by our SI units that a force is composed of a mass times its acceleration. But we're going to get into that later. A force is a vector. Because it's a vector, it's going to show magnitude, which is the number, and direction. So we're going to have positive and negative for our forces, and that's going to tell us which direction it's going. Okay, and we're going to use our convention that this is a positive x, this is a positive y, this is a negative x, and this is a negative y. So if we have a force this way, it's a positive f, negative f, and negative f. And we symbolize a force by a capital F, or later on I'm going to show you different symbols that we're going to use, and it's used an arrow. The length of the arrow is going to symbolize the magnitude, and the tip of the arrow is going to symbolize what direction that force is working in. Okay, well, there's a couple types of forces. We're going to be concentrating on two types: contact forces and field forces. First semester, we're going to be dealing with mainly contact forces. Now, contact, just like a contact sport, you have to have touch. So the forces that we're going to be dealing with when we talk about contact forces are going to be objects that are touching each other. So for instance, if I had somebody standing right here and I were to shove them, I have to touch them to have that shove. So a shove is a contact force. If I were to grab someone's arm and say, come on with me, I have to pull them. Therefore, for me to pull them, I have to touch them or have contact. Therefore, a push or a pull is going to be a contact force. Now we're going to talk about field forces. Those don't have to have contact. So the ones that we've been working on so far is gravitational force. Gravitational force is something that is pulling an object down. So for instance, last chapter we talked about throwing a ball up in the air and having that gravity constantly pulling it down. But the gravity isn't touching the object. The object isn't necessarily touching the earth for the gravity to work. So this is what we call a field or a distance force. We also have an electrical force. So if you were to ever get a shock from someone, you don't necessarily have to touch them. You can just walk by them, and that electrical force is going to jump from them to you, and you're going to feel it. Another example is that the Van de Graaff generator, that thing you touch normally I think in a science museum and your hair stands up on end. If you get near that, you're going to feel the electrical force from that. You don't necessarily have to touch it to have any reaction to it. That's called a field force. The way that we represent forces are by drawing what's called a free body diagram. It can be shortened to FBD, a free body diagram. The way that we show these is we take the object, whatever the object is, and we kind of make it all to be just a square or a circle. So if it's a person, the person becomes a rectangle. If it's a car, the car becomes a rectangle. If it's a box, the box becomes a rectangle. Right now, we're going to assume that everything has uniform density, and so it just acts the same as if it was a symmetrical box, or in this case, a symmetrical ball. Now, the objects truly are not a square or a circle, but we're going to assume that they are. So we're going to draw the forces on these objects using the arrows, the direction that the force is acting. And we're going to label it F sub W, which would be, later on I'm going to show you, we might just put a W here, is the force of gravity. And we have a push over here. And this one, we might have a ball that's hanging by a rope. And so that rope is holding it up here. You're going to have a force of tension. And then the weight of the ball is going to be going down here. So you can have W down over here. Okay, so this is how we draw free body diagrams. And we're going to get into that in more detail in tomorrow's lesson. Okay, so here's an example. Example 1, draw a free body diagram of a person pulling a sled over ice. Now, the reason why we're going to talk about over ice is because we don't have what's called friction, and we're going to get into friction later on. But if I were to draw this person, I'm going to represent the person as a box. Okay? Doesn't really look like the person, but what are the forces that are going to be acting on this person? Well, the person is going to have the force of gravity, and that is always down. And remember, gravity is negative 9.8, so it's pointing negative in the down direction. But this is going to be called the force of gravity, so we're going to say F sub G. Okay? We also have a force, and we're going to talk about it more specifically later, which is called a normal force, and that is going to be the opposite of this, and it's going to point straight up. And in tomorrow's lesson, we're going to talk a little bit more about the normal force. Well, we have him pulling on this sled. So as he's pulling, the sled is going to resist his motion. And so we're going to have this force coming down here, and this is going to be the P, or F sub P. So F pull. Okay, so the sled is actually pulling the guy, just as if the guy is pulling the sled. So that would be a free body diagram of the person pulling the sled over the ice. Okay, now we have a book. Draw a free body diagram of the physics book at rest on a desk. Well, once again, the book becomes a rectangle. Okay? The book is going to have mass, and therefore, because it has mass, it's going to have weight, and we're going to say that the weight is going to come down here. So we have force of gravity or weight. Well, we also have an equal and opposite force, which is called the normal force that I talked about over here. If you were to hold the book out in front of you, you would be able to feel that normal force. And we're going to talk about that, like I said, in more detail in tomorrow's lesson. But this object is going to have a normal force that's going up here. And there's nothing else acting on it. It just has these two forces. Okay, and our third example. What about a free body diagram of a football being kicked? Now we're drawing it of the football, not of the foot. So we're going to, in this case, we can make it a rectangle if we want, or we can make it a circle. But what forces are going to be acting on it? Well, the football is going to have mass, and so we're going to have the force of gravity down here, F sub G. And we said that we also have the normal force that's going to go up here. But this football is being kicked. So there's a force of the foot onto the football, and you're going to have a force of a kick, okay, or a push or a pull. We can just do it this way. and this is what's going to be shown. Now you can see that the arrows represent the direction, so the kick is going to be kicking it that way instead of straight out, because if he was kicking it this way, the ball wouldn't go up in the air. We're hoping that he's going to kick it up here. So this is our free body diagram of the football being kicked. Okay, so we're going to talk a little bit about some misconceptions about forces. Can an object continue to accelerate if no force is acting on it? Okay, well, if you don't have a force acting on it, then there is not going to be a change in velocity. And if there's no change in velocity, that means there cannot be an acceleration. So, can an object continue to accelerate if no force is acting on it? No, it cannot. Okay, so later on, we're going to be talking about forces and what is the acceleration. We have to make sure if there's no acceleration, there's no force acting on it. Can an object continue to move if no force is acting on it? Well, now, can it have velocity? It can have velocity and be moving and not have a force acting on it. So this would be an instance of a car set in motion on speed control. It's moving, but it's not changing its velocity, therefore there's no acceleration, therefore there's no force. So yes, an object can continue to move and have no force. Okay, what is the acceleration of an object moving with constant velocity? Well, if the velocity is constant, it means it's not changing. So the velocity at this point is equal to the velocity this point, so our acceleration, which is the change in velocity, is 0. Okay? And a free body diagram only represents the forces acting on the body. Okay, so for instance, of the football being kicked, we did not add the force of the foot. We only added the force that the football feels. Okay? If we were going to be talking about the person pulling the sled, we did not add the mass of the sled into that. Now, if I were to draw a free body diagram of the sled, that would be a different situation, and we would take into the mass of the sled, but we would not include the mass of the person. So remember that the free body diagrams represent only the forces acting on the body, whatever the body is, whether it's the person, whether it's a sled, whether it's a box. Okay, so now don't forget to do the Edline assignment, and tomorrow in class, or Monday on class, we are going to be doing a lot of free body diagram drawings and continuing on. We'll see you tomorrow.